In this lesson, we're going to talk about the three main types of radioactive decay, and those are alpha decay, beta decay, and gamma radiation. So let me actually just write that right here. So it's alpha decay, beta decay, and gamma radiation. Oof, it's moving that all the way here. Alright, so let's pull this back. Alright, so before we get into each of the decays, we have to review a few of different types of particles for this unit. So this first particle is the alpha particle, which has two ways of writing it. So remember, alpha, if you write an alpha, it looks like this. Alpha looks like this. Looks like a little fish to the side. But that's the Greek letter alpha. So for alpha decay, there's the alpha particle. And the alpha particle has two protons and two neutrons. So let me write that. Two protons, let's put a P plus, and two neutrons. So if you think about it, the atomic number, if it has two protons, then it's going to have an atomic number of 2. If you put the in nuclear notation. And if it has two protons and two neutrons, then the mass number would be 4. So this is one way of writing the alpha particle. But if you also look at it, if it's got 4, 2, what other element has two protons and a mass of 4? If you look at your periodic table, 2 protons and a mass of 4 is helium. So we can actually just, this is the same thing, I should write it right here, is the same thing as 4, 2 helium. So in alpha decay, you can see either this 4, 2 alpha, with the alpha decay particle, or you can see it as a helium, written as a helium. Quick note, you should know that this actually has no electron, so it's got a charge of +2. So the first type of decay, alpha decay or emission, is the emission of an alpha particle from the nucleus. So let me draw that. Actually, I'll keep this right here. Let me draw the emission from a nucleus. So let's say you have a atom. We'll put there's like electrons, and then this is the nucleus right here. So in alpha decay, what happens is you get a 4, 2 helium kicked out. So you get 2 protons and 2 neutrons kicked out. That's what emission is. So the original atom loses 2 protons and 2 neutrons, so the mass is going to be reduced by 4, while the atomic number reduces by 2. So I'm going to show you an example here with the alpha decay of radium-223. So I'll write that here. Alpha decay of radium, just put Ra-223. So let me bring this down here so I give myself a little more room to work with. So from when you write the alpha decay of radium-223, what you got to first figure out is find out the symbol and the atomic number of radium. So radium right here, the symbol is Ra, it's got an atomic number of 88. It says right here that it's got a mass of 226, but what's given to us is a difference in isotope, so we're just going to use what's given to us, which is 223. So we have radium, right? That was, let me make sure that was 88, yep. And that's the atomic number, and then atomic mass, we're just going to use the same thing that we are given, which is 223. So if you do the alpha decay, you could write it either as two ways. You can do the 4,2 and the alpha, or you can do 4,2 helium. I'm going to do the 4,2 helium. So basically, it's like an equation. You have 223 on the top, and basically you get rid of 2 protons and 2 neutrons, so you're getting rid of a mass of 4. So you think about 223 minus 4 is going to be 219. And then you're going to get rid of 2 protons. Remember, 2 protons are gone, so it's 88 minus 2 is 86. And so when you look at your periodic table, what element has an atomic number of 86? That's going to be radon, Rn. So we'll just put an Rn right here. And that's all alpha decay is. Another particle note is the beta particle, which actually I'm going to pull this down right here. So let me actually just write here. This is going to be beta particle and beta decay. So the beta particle is what's used in beta decay. So the beta particle, you can actually draw it like this. It's going to look like this. It's going to have it. It's going to be E. It says 0, -1. It's basically an electron. So a beta particle is, yeah, it's essentially an electron. In beta decay, a neutron, so let's say you have a neutron, I'll put a little n right here, neutron, splits into a proton, so that's got a plus, and an electron. So basically a neutral atom, or not an atom, neutral particle, subparticle, splits into a positive one and a negative one. And so the original atom is going to gain one in atomic number because it gains a proton, right? Because the neutron turns into a proton. And it actually keeps the same mass because the neutron and proton have the same mass. So I'm going to show you an example of the beta decay of iodine 126. So I'll actually just type it right here instead. So let's pull this over here. All right. Beta decay of iodine 126. Remember that 126 is representative of the mass of iodine. So let's pull up a periodic table and let's see where iodine is. Iodine is right over here. It's atomic number 53. And a mass number says 126.9, which would round to 127, but again, we're using an isotope, which is 126. All right, so let's write out our equation. So we're going to start off with what we know, which is we have an iodine. It's got a mass of 126, and the atomic number is 53. Let me make sure. Yep, it is 53. And what's going to happen is a beta decay. So in beta decay, you always are going to write the beta particle first. So you have that 0, -1 e. That's basically an electron being kicked out. And so then what do you have left over? If you think about it, you're going to gain a proton, and the mass is going to stay the same. So think about it, 126, and if it's like an equation, 126 minus 0 is still 126. It's going to be 126. And if you think about it, 53 minus -1, it's going to be basically adding 1. So this is going to be 54. So if you look at your periodic table, let me pull that up again. So iodine went from 53 and now gain a proton, so now it's actually xenon. All right, so that's 54. So we're going to make this an Xe. And that's what happens in all beta decays. So related to beta decay, there's actually something else called a positron, which I'm going to show right here. So we have a positron is basically is a positively charged electron. Positron is a positively charged electron. And so this is a type of antimatter. So this is antimatter. And it's going to show up, it's going to look like this. How electrons were 0, -1 e, this is going to be a 0 + 1 e. So the exact opposite, it's the opposite, it has the same mass, but it is the opposite charge. So that is antimatter. We're not going to focus too much on that, but it's good to know that it exists. So when you have something like matter and antimatter come together, so in this case this is antimatter, and let's say you add that to normal electrons, 0, -1 e, it's actually going to become a gamma, it's going to turn into gamma radiation, which is just this. And sometimes for gamma radiation, I like to put 2 zeros here because nothing changes, just a lot of energy right there. So the last type of decay we're going to talk about is gamma emission, which is when a nuclide, so that's like any atom, is in an excited state, that's usually marked with asterisks, and releases a gamma ray to go down to ground state. So I'm going to show you an example right here. It's going to look like almost nothing happened, but actually a lot of energy is released. It's actually what's in nuclear bombs and such. So I'm going to do an example with strontium-87. So I'm going to do SR, remember 87. This is going to be the gamma decay of strontium-87. And remember, strontium, if you look at your periodic table, has an atomic number of 38. So in gamma radiation, you always have the little gamma. And remember, there's going to be this little star to show that it has a lot of energy that needs to be released. It's gamma. And I like to put a 0, 0. Because all it ends up showing in the final is it's still going to be strontium with the same numbers, atomic number and mass number. It's just a lot of energy was released, and it's actually the strongest type of radiation. And last but not least, the last symbol to mention is the neutron. which is actually just looks like this. So a neutron just looks like this, which is going to be a 1, a 0, and an N, showing that it has a mass of 1 because a neutron has mass, but there's no protons in a neutron, so it's just 1, 0 neutron. And you might see this a couple times in problems where a neutron is lost.